Hello everyone, this is the review of the lecture on neural networks. So the problem is that in many applications we don't need really a complete basis, but only a few basis functions if they're tuned correctly. So let me show you the architecture. So this might remind you of the architecture I've shown you in the lecture on fixed basis functions. So we have an input layer, dimension m. X naught is always the constant, the 1. Then we have connections to all the units. In this case, they're called neurons in the hidden layer. They go through nonlinearity. They calculate an output, and then we have a weighted sum of these hidden layer neurons. Maybe we have another offset here, and this can be the output, or we put another threshold on top for a classifier. And these basis functions, they assume a very specific form. They have a characteristics which reminds a little bit of the transfer function of a neuron, a biological neuron. So it's calculating. So this is the one-dimensional case, V naught plus a constant weight multiplied by x. And then we apply the sigmoid on top of this linear expression. And the sigmoid is mathematically defined in this form. It's 1 divided by 1 plus e to the minus argument. So argument would be here vx plus v naught. And it has this form. So this is with these parameters, sigma of 1/2 x minus 25. So you have somewhere like this sweet spot where you have the transition from -1 to 1. And by adapting these parameters, you can make this transition more steep or less steep, and you can move it around in space. Then this corresponds a bit to a neuron which doesn't fire if it's not excited. It has a maximum rate of firing if it's completely excited, and then there's some more or less linear transition between these two states, two phases. So this is the whole expression for a neural network with a single hidden layer. So these layers I showed you are called hidden layers. Here, these guys. So it's so this is the one input case, but let's go to this input here. This is the more general case. So the output is a weighted sum, and here we now use h for the number of hidden units because it was m phi, before it m phi. So it's a weighted sum. The weights are wh, h is the index, and this is the basis function. So it's a sigmoid applied to a linear weighted input. So you have these synaptic weights. Here you have the offset, and then here you have another synaptic weight here at the output. And this is already quite powerful. And the important thing to understand is that before we sort of had fixed parameters or smartly or cleverly chosen parameters to determine the functional form of the basis function. And in a neural network, we are adapting not only the output weights, so that's what we're also doing, but we're also adapting the so-called input weights from input to the hidden layer, the V's. And by doing that, we have this additional flexibility that the neural network, when we fix the number of hidden units, for example, has the ability to find its own optimal shape of basis functions. And that's really the key. And this particular form of a sigmoid is also interesting because it says in some parts of the input space everything is sort of boring, then there is some interesting part, and then there's a boring part again. And with a few neurons you can, for example, model this complex function. Okay. Yeah, we talked about the architecture already. Yeah, there are different variants. So if you use it as a classifier where you separate two classes, 0 and 1, or 1 and -1. So in this case, 0 and 1, you apply a sigmoid, an additional sigmoid at the output. So you have another sigmoidal function here. And if you do multi-class, you can simply have several sigmoidal outputs. That's how it was done initially. And nowadays they have these softmax transfer functions, which guarantees that the outputs are positive and sum to 1. So you can interpret them as posterior class probabilities. And so for this latter case, if you have several classes, the architecture looks like this. You have inputs again, you have a hidden layer, and now you have for each class a separate output. And that has some advantages, that you are sharing resources and defining the shape of the hidden units, and you only have individual sort of linear classifiers here on the output layer. And as I said before, nowadays typically people don't use the sigmoid, but the softmax transfer function at the output. Yeah, initially people also used the squared difference, squared error between prediction and and target as a cost function, the difference squared. Also today they're using the softmax cost function or the cross entropy cost function. So this is the tedious equations of how to adapt the parameters. So I don't want to go through this again. But essentially we end up with stochastic gradient descent, where we adapt each parameter so it goes in a direction that it minimizes the cost function, but since it's pattern by pattern based, it will only go on average in the right direction. But this stochasticity has also advantages. So the learning is fast. The moment you calculate something, you can update the weights, and it also avoids a little bit the problem of local optima. You can do weight decay. Here was an example we went through. Softmax cost function. Yeah, this is a very smart way of doing regularization. You observe the training error, which should go down. So one epoch means you go once through all the data points. Typically, since the optimization or the learning is an iterative process, you have to do that several times. And then you observe the test error or some data you don't use for training. At some point, you see that the performance becomes worse. And if you then go back, in this case, to epoch number 5 and take the weights which were active at that instant in time, then you're not overfitting, because this is so-called an overfitting effect. The idea is that you start to model the noise, which doesn't have any valuable information, and yeah, we've seen this before. And it looks like you typically end up with weights which are smaller than the weights which you would end up if you would optimize all the way to the end. So you can also think of the stopped learning or stopped training as a weight regularizer. Yeah, you have to be careful picking eta, the learning rate, carefully. If you're too small, then you never converge. If it's too large, you have instability. But fortunately, there are smart algorithms which help you, like Adam, which we cover or discuss next. And there's a lot of worry about local solutions that because the updates, stochastic gradient descent, and these gradient-based methods, they can end up in a local optimum. And here and from here, it looks everything is fine in any direction. I will increase. So the algorithm might think it's done, and it doesn't know that there's a better minimum over here. It turns out in deep learning with many layers, this is not such a severe problem, and also that stochastic gradient descent helps you avoid this problem because through the stochasticity, you sort of avoid getting trapped in local optima. Then we looked at some of these approximation errors people have derived, and I think this is an interesting results from Barron's work, that the number of hidden units, so you pick a class, a target class, where you make assumptions about how the target functions are generated, and there you assume a certain smoothness. So in this case, that this integral over the weighted Fourier transform is smaller, limited by this factor CF. And under this constraint, then he could show that the number of hidden units is on the order of 4 divided by epsilon m square. So epsilon is the error you are willing to tolerate. If it's smaller, then you need more hidden units. And m is a smoothness parameter. So if it's smoother, you need fewer parameters. And the important thing is that m doesn't appear in this equation at all. So the number of input dimensions is not important for this estimate of the approximation error. Whereas if you remember for the equation for the number of fixed basis functions, it was on the order of 1 divided by epsilon, and then m divided by m. So m is the number of hidden units, m is the complexity in the exponent, and this gives you this explosion of required basis functions if you use fixed basis functions. So this, it might or it might not be something attributed with this particular form of basis functions that you're using, the sigmoidal basis functions. It's definitely not a bad choice, but probably more important is that a neural network has this adaptive way of finding the best basis functions in the backpropagation learning algorithm. Okay, thank you very much. This was the review.